Good day, my name is Misha. I'm from Labs. I'm one of the developers of Embedano, and Embedano is a Rust SDK for embedded devices for communication with Cardano network. And today I want to show you the demo of our milestone 4 submission, and this demo will demonstrate transaction streaming. The source code can be found in MLabs repository under the Embedano, and branch is example stream demo, but probably when this video will be published, everything will be merged already to main and development branches. The full documentation for this submission can be found under the milestone 4 documentation, but if you didn't see the demo for milestone 3, I would recommend to go and check it out first. It can be found in milestone 3 documentation under the links section. And the reason is because the current demo is built on top of the previous one, and it's actually modification of the example project we prepared for milestone 3. With that difference is that instead of calculating transaction ID on the host side and then signing it with device, we stream transaction body to the device, and whole verification process and transaction ID calculation happens on the device. And then if user accepts calculated transaction ID, it will be signed to the device and sent back to the host. So this approach gives more security guarantees to the user who gonna use like hardware wallet or other embedded device with Embedano SDK. And couple words about streaming itself. Why do we even need it? The issue is that embedded devices has limited resources, and in terms of transaction signing, the biggest concern is memory, because Cardano transaction can be big enough so it won't fit into the device memory. And this is known and mostly solved problem. You can find more info about it under the Cardano CIP 21 documentation. And in 2 words, the current solution is build transaction, unsigned transaction, then modify transaction body in some standardized way. And then instead of sending the whole body to the device, send it piece by piece in sequence in standardized order. And then device, when it receives each entry, it will add it to the rolling hash calculation. And when full body is streamed to transaction, when there is nothing left to stream, device will calculate final hash, and this hash will be transaction ID. And then this transaction ID can be signed, and signature will be sent back to the host or client application, and the host application will produce the final signed transaction and send it or submit it to the network. And during this streaming process, device can demonstrate to the user like different parts of transaction he's willing to sign. For example, inputs, outputs, fee, or asset values. And user can either confirm or reject each entry. And of course, if single entry is rejected, then the whole signing process will be cancelled, and device will go back to like waiting mode, waiting for new messages. It's worth noticing that there is tools available to make this transaction transformation, but not each transaction can be transformed this way. So it's something to keep in mind. Not every transaction that can be accepted by the node can be processed and signed by embedded device, at least at the moment. So our goal was to add transaction streaming to Embedano SDK, but during the development process, we figured out that support of the streaming for the whole transaction body requires big amount of work, and we just had no enough resources left at our disposal. So we implement stream only partially. We try to set up like some base that can be extended in future. So let's jump into the code to see more in detail. This is core SDK library, and we extended it with TX stream module, and now it's pretty concise. As you can see here, currently it allows stream only transaction input, like transaction hash and index and fee. And this is a related part of the communication protocol, where we can either send transaction entry, like input or fee in our case, to the device, or signal that streaming is done and we want to calculate final transaction ID and sign it. So this part can be extended to support REST parts of the transaction body to enable like full streaming capabilities for embedded devices. And how communication set up at the moment. The host application connects to the device. Then it asks public key from device. Then it asks available UTXOs for this public key. In the pre-production network, build and sign transaction, and then stream transaction body to the device. Well, in this case, only partially. It streams only inputs and transaction fee, as you can see here. And let's actually jump to the client code. Client code is located in examples. nrf52 stream client. So we can jump into the device and scroll down to stream TX section, and here you can see we stream inputs, and then stream fee, and then we signal to the device that stream is over and we want to calculate final transaction ID and sign it with password and key for this derivation path. And device in its turn process each of these entries, and for all of them it sort of prompts the user to either confirm or reject the input. But as you can see on the right top corner here, there is no screen anywhere on the board that we're using for this project. So we emulated the screen in debug logs on the firmware side, and you will see them under the live demo run. So as I mentioned earlier, the code base is a modification of our previous demo. The biggest difference is that we no longer calculating transaction ID on the client side, but instead stream transaction body to the device and get transaction ID there and sign it from the device. So there is sort of no man in the middle between the transaction body and the final signature that we want to use to submit transaction on chain. So there is more security guarantees, and this is how all hardware wallets operating now. And before we run a live demo, let's get a quick look onto the client side actually. And here we building transaction, getting key from device, getting UTXOs from wallet address, and then make and sign transaction here. And here we stream transaction body to the device. And there will be like 3 rounds of streaming just to show every possible outcomes when we can reject or confirm inputs or transaction ID. And another difference from the previous demo is that device now initialized 2 buttons. They're here, button 1 and button 2, and 1 button for confirmation and 2nd button for rejection. And if any input is rejected, the process cancelled and starts all over again. To run the demo, there is a shortcut, stream demo sh, and it runs package of stream client with some arguments we prepared. This is actually a seed phrase for the wallet that is available on pre-production network and funded and can be used to try things around. And the only thing we will need from the host side is socket to Cardano node and serial port of the USB device. I'm not gonna go again through setting up everything. You can again check it out in the demo for milestone 3. At the moment, I have device already flashed. It is here on the left side, and it awaits incoming messages from the host. And to start the host, we're gonna run this demo script. So let's examine the output. As you can see here, host got the message that device was initialized successfully, and we can see it on the firmware side that device was initialized with mnemonics. And now it sends public key back to the host, and host need this public key to build proper transaction. And on my setup, probably because this is WSL Debian inside of Windows 11 with some serial port forwarding, it takes some time. But now we see that host finally received public key, and it starts streaming this like first round of streaming, and we can see on the left side of the device this improvised display. The device asks user to confirm this input, and we can press buttons to either confirm to reject. So let's confirm input. We see that we proceed to fee, and fee is this much. And let's just for the demo purpose reject the fee, pressing button 2. And on the host side, we see that we receive transaction confirmed message, but for the fee, host application receive an error. It canceled the whole process and started the 2nd round of streaming. And on the device side, we see this like new round, and device again asks user to confirm input. So let's now confirm input. Input is confirmed, and confirm fee as well. So now the so to say, partial streaming is over, and device host application signals to the device that stream is over and we want to calculate transaction ID. And here device calculates transaction ID and asks user to approve this transaction ID. But this time we just reject it, and we see that host again receives an error and goes to the third iteration of the streaming for this demo. And again, on the left side, we see that things started all over again. So let's confirm input, confirm fee, and pretend that this is correct transaction ID, and confirm transaction ID also. Now when transaction ID is confirmed, the signature was created, and device sending signature back to the host, and host here it asked to finalize stream and sign transaction ID, and now it waits for the signature. So let's just wait while it will be finished. Sometimes it takes a while on my setup. Okay, now streaming is finished, and we can see that host receive the signature, and the signature can be used now to build final signed transaction. And this is also how all hardware wallets operate. They like stream transaction body to the device, then confirm and sign transaction ID, and then send signature back. And this is the responsibility of the host to construct final transaction with signature and witnesses. And this is actually it for the demo. There will be a gap analysis in documentation and some improvements within that can be added here. Well, obviously, implementing the full streaming is the first gap that we have, but we hope that the base we set up can be easily extended in the future, and the rest of our ideas and concerns we will add in the documentation of the milestone 4. That's it from my side, and thank you for watching.